Hi guys, so this video is going to be about how to calculate wave speed, but before we get to that, I figured that we would review something we went over on Thursday because the homework assignment does ask questions about this. So I just wanted to remind you, when we're drawing waves, the dotted line is like the resting position or the equilibrium position. It is where the medium would be if there was no wave happening through it. So whenever we talk about anything, when we draw these waves, we're always drawing from the middle or to the top or middle to the bottom. So when we're figuring out more energy, these two waves have the same amplitude, so they have the same height above that equilibrium position. I mean, I freehand drew it, so ish. We're going to pretend they have the same amplitude. But this one has a lower frequency than this one. So this is a wave that's occurring more often. So in the same amount of time, this one has one wave, two waves. So there's two waves total here. And this one has 1, 2, 3, 4 waves. So this has a frequency that is twice as high. And if you think about it, that means the wave is happening. The vibration is occurring in the same amount of time, twice as often. So that means if you had your little medium, it has to move back and forth more times in the same amount of time. So it has to move more. So that means it would have more energy. It would have more energy. Okay. So high frequency always has more energy. Okay. So this is the one that has more energy. That one. But also amplitude has a part to play in this as well, because if I have the same frequency in both waves, so here I have two waves here and two waves here, the amplitude in here is not as high, whereas the amplitude here is much larger. The wave looks like taller. And that means that even though if this is my little particle that's vibrating, here in the same amount of time, it has to vibrate a greater distance. So here it was vibrating more often. Here it's vibrating a larger amount. So that would take more energy. So this one has a high amplitude. So it's the one that has more energy. So again, that's just review from something we talked about on the block day, I think. So that's the first thing I wanted to mention because the homework assignment does talk about that. But what most of this is about is how to calculate wave speed. So wave speed, Google keeps telling me that I'm spelling it wrong because it says it should be 2 words. Google is wrong. The textbooks spell it as 1 word. But they use the same symbol for this as they do for velocity because it's still a speed, it's still a velocity. But we're just in the context of waves. So if you remember from way back at the beginning of the school year when I was not here, you calculate average velocity if it's a constant velocity, which waves honestly usually are, as your change in position over time. Okay. Now, this is just a distance over a time. You've seen this many times before. In the context of waves, we would replace this, what's the distance that I usually measure with waves, and that is wavelength. Okay, so that's the length of one wave. So remember, a wavelength is one up and one down. So that's one wavelength, which we abbreviate with the Greek letter lambda. And one wavelength would occur in the time it would take for one wave to go by. So it's wavelength per period. Okay. Generally speaking, period is actually not a variable that's that easy to measure, and we don't like fractions. So usually this is rewritten. We can put the period as 1 over t times wavelength, and then 1 over t, remember you have an equation for that where the frequency is equal to 1 over t, and so then this becomes frequency times wavelength. And this equation is on your equation sheet, which I've been attaching to every assignment in Canvas that you would need it for. So it'll be on this wave speed assignment as well. And it's a pretty simple equation. But there is one thing I do want you to be aware of that's not always mentioned, and that is that even though you can use the frequency and the wavelength to calculate the wave speed, neither one of those factors actually influence the wave speed. And you might have figured that out from if you've already completed the wave speed conclusion. But if you haven't, I'm giving away answers. So it turns out if you change things about the wave, you don't really change the wave speed. Like if you change the amplitude, if you change the frequency. But if you change things about the medium, like is it going through metal or plastic or liquid or air, or the temperature, like things like that, tension was one. Those things can change the wave speed because you're changing things about the medium. But in this case, if I increase the frequency, so if I have a really big frequency, it turns out I just get a really small wavelength. And you've seen that before. I actually just showed, I should have kept that last picture. So if this is my wave, my frequency is low and my wavelength is long. Whereas here, my wavelength is getting shorter with my increased frequency. So if I have a large frequency here, that means the wavelength is smaller. The wave speed stays the same. Okay, it stays constant. And the opposite is true as well. If I have a small frequency, the wavelength gets really big so that the wave speed can stay the same. So if you know properties about the medium, that influences the wave speed, but the frequency and the wavelength do not. But because they're always proportional to each other, they still always come out equal to the wave speed, which is really convenient. I hope that makes sense.